All right, we should be all set and ready to go. Good morning. This is Wednesday, April 29th. Hopefully you're all having a great day so far. It's about to get even better because we're going to be learning some rational functions today, more rational functions today, in addition to what we've already done. I even have a do now for you today. If you could factor the following expressions while I just go through my little reminders and my little spiel about the progress assessment, that would be super appreciated if you could go ahead and do that. So, quick little factoring while I go through this stuff. Number one, make sure that your microphone is muted and your webcam is off, which most of them are. I think everybody's got used to that, which is great. Make sure you fill out the attendance form on Google Classroom. That's very helpful. We need to make sure that you're present for the day. And just a quick reminder about that progress assessments, the first one of quarter 4. It is due back to me by Thursday night at midnight. So that way I can spend Friday to actually grade it and get back to you. So please make sure that you get that done if you haven't gotten that done yet. I know I've gotten probably about a third of them back so far, which is great. But, please make sure you get that done when you have the opportunity to get that done, okay? Anything that we do today is actually not going to be on that progress assessment. That's why it was assigned Monday. It was stuff that we've already done from Monday's class and before. So this is officially new stuff. So there's that. But if you do have any questions at any point, please reach out to me. I want to emphasize the fact that Miss Mao also has dedicated office hours for Algebra 2 extra help and other classes, but Algebra 2 is one that she does as well, so you can go ahead and join for some extra help on that. You can reach out to me at any point for extra help if you need it. And that's pretty much it, all right? But I appreciate you all coming here on this fantastic Wednesday morning. So let's go ahead and get rolling. Today, what I'd like to do with you is actually show you a couple more rational functions. These rational functions being a little trickier, one additional little twist that we can throw in to these types of rational functions. All right, and you'll see what that is in a little bit. Our do now here was talking about a little bit of factoring. Factoring at this point in Algebra 2 CP, especially with expressions like this, I don't think should be a major intellectual milestone because we've been factoring all along. From like October, so it should be a pretty straightforward process, but factoring is going to come back in a big way today to actually combine with our rational functions that we've learned already, and you'll see hopefully how that can produce some pretty interesting looking graphs. So starting with our first expression over here, if we were to factor x squared minus 2x minus 8, how would I do that? Well, I need to break it up into two binomials, just like this. I need x and x to multiply to x squared. Since we're multiplying to a negative at the very end, we do need different signs, one positive and one negative. And what factors of 8 will somehow combine to give us 2? I think that's minus 4 and plus 2. Okay, so that's how we'd break down something like x squared minus 2x minus 8. Next, we got x squared plus 13x minus 12. Again, we need x and x to multiply to x squared. Keep in mind, if it were 2x squared, we would need 2x and 1x. Here, everything's positive, so it makes sense to just keep everything positive. Why introduce any negatives into that at all? And since we're multiplying to 12 at the end, we have to find factors of 12 that combine to 13 when we do our distribution. That's just going to be 12 and 1, because 12 plus 1 makes 13. Last but most certainly not least, we have x squared minus 11x plus 30. We need x, we need x. Since we're multiplying to a positive, both the signs have to be the same. And since our goal in the middle is to combine these like terms to actually achieve a negative result, it makes sense to have two negatives. And what factors of 30 are going to result in us getting that 11 in the middle? That's going to be 5 and 6. Just like that. Okie doke. Any questions, comments, concerns about that at all? Feeling good? Doing great? Okay, fantastic. Now, let's actually take a look at how that's going to intermingle with our rational functions that we've been doing already. You might be like, well, how is this relevant? Oh, you shall see, my friends. You shall see. Take a look at a graph like this. Ready? Let's sketch a graph of f of x is equal to x plus 1 divided by x squared minus 3x minus 4. Oh boy, the fun begins. We got a little bit of factoring going on and something like that, yes? So if I'm actually taking a look at that problem, yes, it is true that you could jump into a problem like that without doing any factoring or simplifying, but why would you? Hopefully your Algebra 2 instincts are kicking in upon seeing something like that, and you're like, ooh, wait a minute, I should probably factor that down, particularly the denominator, and see if I can simplify that expression at all, right? Because that's probably a good idea. Let's see what that's going to do. So if I factor the denominator, we can rewrite this expression as x plus 1 over x and x in our two binomials. We need 1 negative, 1 positive, and I believe we need minus 4 and plus 1 in order to factor that down. Now, if we were actually in class still, physically, what I would be doing is I would do my good old scan the class, look back at the board, and go, whoa, whoa, do we notice something here? X plus 1 in the numerator, x plus 1 in the denominator. Oh yeah, those factors can cancel out. And that leaves us with a much easier function to work with, 1 over x minus 4. Okay? It actually works very similarly to the radical functions that we take a look at, where, remember those square root functions and cube root functions where we could go ahead and take a GCF, pull that to the outside, and then our function simplifies significantly. The same exact idea is being applied here. All right? So, one second, I'm trying to set something up for you here while I'm talking. All right, so that being said, now we only have to worry about this little function instead of that big complicated function, so we can go ahead and find the vertical asymptote. The vertical asymptote here would be x equals 4, because 4 minus 4 in the denominator would result in dividing by 0. Your end behavior asymptote, compare the degree of the numerator and denominator. The degree of the denominator is larger because it's x to the first versus no x's at all, so our end behavior asymptote would just be 0. Plus the vertical shift, but there is no vertical shift, right? There's no number on the outside. So it's just y equals 0, which is the x-axis. Okay? So if I go ahead and sketch a graph of that, let's see what that's going to look like. I want to leave a lot of space over on this side because my vertical asymptote is at 1, 2, 3, 4 right here. My end behavior asymptote is at 0 right here. I'm going to try to draw this in as accurately as possible. That's on the x-axis like that. Okay, and now I'm going to go ahead and test some points. Just like before, just like the functions we've been doing. Okay, so let's see, the vertical asymptote is at 4, so let's go ahead and plug in 2 and 3, as well as 5 and 6. That's just 2 values to the left and 2 values to the right of that vertical asymptote. So 2 goes into my function. By the way, now that we simplified this complicated function to this much easier looking function, we don't have to plug into the top function. You certainly can, but it's unnecessary. Like, you're just going to get the same answer if you plug into here versus if you plug into here, so why not just go with our simplified version? I take 2, I plug it in, we get 1 over 2 minus 4, which is 1 over negative 2, which is negative 0.5. Right? So I got a point at 2 comma negative 0.5. Right about there. 3 goes in. I get 1 over 3 minus 4. 3 minus 4 is negative 1. 1 over negative 1 is negative 1. 5 goes in. I get 1 over 5 minus 4. That's 1 over 1, which is 1. And lastly, 6 goes in. I get 1 over 6 minus 4, which is 2. 1/2 is 0.5. Right there. Okay? And then, hopefully, you can actually even visualize at this point what your curves are going to look like by seeing a lot of different examples. Our curves are going to approach the asymptotes, but not touch them, right? They're going to approach, but not touch the asymptotes. Does everybody see how that works out? Does anybody have a question as to how that works out? Feeling good about that? Ooh, I heard a beep. I heard a beep. Feeling good, Sean says, feeling good. I have something to show you, though. Very fancy right now. Like I said, I was trying to set something up for you. Take a look at this. Rather than draw the graph on paper, let's go ahead and I'm going to transition to my other layout. I realize I'm on pre-calculus right now. This isn't pre-calc. This is Algebra 2. This is Algebra 2 CP. Why are we on the pre-calc layout? What is going on here? I am going to transition to actually another layout. My AP Computer Science layout. Look at this. We actually have the digital version of the graph up on the screen. Ooh, fancy, fancy, fancy. So let's take a look at that, right? You should be able to notice that here's our vertical asymptote at x equals 4. Here's our end behavior asymptote at y equals 0. And our function is going to approach, 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 but never touch the asymptotes. Approach, 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 but never touch the asymptotes. So this function behaves just fine. It's just like you'd intend or expect it to behave, with the exception of one little bit of weirdness. If you were to click and drag, clearly you can see that if I plug in any value for x, I get any value for y, right? It shows the x value and the y value associated with this function, except for this one. Yikes. It's hard to actually keep my mouse there. I was struggling with this yesterday with my A1 class. There we go. Yikes. Yikes. -1 in this function is undefined. There is an undefined point, a singular undefined point at x equals -1. Well, why is that the case? Well, what happened was, going back to our actual problem here, let's get out of this, get out of this. We got all the tech going today. No full screen. Back to A6, not pre-calc, which we were on for whatever reason. If we actually look at our problem, the reason why we have that singular undefined point at x equals -1, is because of this cancellation. When we canceled out a factor of x plus 1 over x plus 1, that unfortunately comes with a price. And the price is that it creates this singular undefined point at x equals -1. Okay? Now, the reason why that all happens is because what we do when we simplify a function like this down to a function like this is we're essentially saying we can represent the graph of this function with the same graph as this function, with the exception of this point right here. Because if you notice, in our original function, if I were to plug in -1 before the cancellation actually happens, -1 would still result in dividing by 0. You still have this factor of x plus 1 in the denominator, so that if I plugged in -1, that would still be a problem, right? So we are sketching a graph of our original and not this revised clean version, so we do have to account for that one singular undefined point. And there's a name for those one singular undefined points that happen to show up, and the name for that is, it's called a hole. So I would say that there is a hole in the graph at x equals -1. And the reason why, again, it's at -1 specifically is because we canceled out this factor of x plus 1. -1 plus 1 would still have caused dividing by 0 in our original function. Just because we reduced it means that, hey, we can represent the graph of this with this, which is way easier, but we just have to account for this singular undefined point. All right? And again, that's referred to as a hole. So just to define it for you officially, a hole is a singular, definitely add it to your notes, undefined point on a graph caused by canceling out a matching factor from the numerator and denominator of a rational function. From the numerator and denominator of a rational function. Okay? So a hole in the graph is, again, a singular undefined point on a graph caused by canceling out a matching factor from the numerator and denominator of a rational function. Okay, so that's what a hole is. The way we represent that in the graph is we draw our curve just like normal. So I'm going to draw this curve, approaching but not touching the asymptotes, approaching but not touching the asymptotes. But wherever my graph, wherever my curve happens to cross this threshold of x equals -1, which in our example would be right about there, I'm going to go ahead and indicate that with an open circle, just to indicate the fact that there is a singular undefined point known as a hole at x equals -1. Does that make sense as to why that's the case? Oh, another thing I'm just noticing as I put it up on the screen, I didn't even update the date. How ridiculous is this? What kind of 2-bit operation are we running here? I didn't even update the fact that today is the 29th instead of the 28th. Come on. Come on. What kind of show are we running here? Jeepers crow. All right, there we go. Okay, I should hold myself to a higher standard than that. Okay, does that make sense to everybody how that works out? Alrighty, fantastic. Okay, so again, just to emphasize, a hole is a singular undefined point caused by canceling out a matching factor. That hole specifically in this graph is at -1 because we crossed out this factor of x plus 1, and -1 plus 1 is what would have caused division by 0 in the first place. Okay, the way that we indicate that hole on the graph is wherever our function happens to cross this threshold of -1, we go ahead and just indicate that with an open circle. Now, there are a lot of misconceptions as far as these holes are concerned, and I want to make sure I clarify them now. Okay, again, if you happen to have a hole at x equals -1, that occurs wherever your function happens to cross this threshold right here of x equals -1, right? That's the line of x equals -1. It's all the points that have x coordinate 1. Your hole is wherever the curve happens to cross that. So consider that if our function was like way up here, if it crosses here, that's where you put the hole. Okay, just like that. If it crosses down here, like say we have a function that looks like this, then the hole goes down here. Okay, a common mistake that students make is when you hear that, oh, there's a hole at x equals -1, a lot of students will just put it right on the x-axis. That's not always, actually, that's very rarely going to be the case that it actually hits the x-axis. It's just wherever the curve happens to go through this -1. That doesn't mean it's also going to go up and intersect at -1. A lot of students do that. They're like, oh, well, there's a hole at -1, so the curve has to come up and hit that. Not the case at all. It's wherever, just in the natural shape of the graph, just the natural curve. If you follow the curve, it's wherever it would just happen to cross this threshold, that's where you indicate the hole. Okie doke. So that's all. That's all really there is to it. But just keep in mind, it's not on the x-axis. It doesn't mean your graph is going to go through the x-axis at that point. It just means that point may be not even very close to the center of your graph, as you can see up here, where that point is way over here, and our graph is really focused on this region. It just is wherever the graph happens to cross the x-coordinate of -1, that's where we indicate the open circle. All right, good. I just wanted to make sure I was very clear about that. Okay, now let's actually take a look at another example. All right. One more example today we can probably get through. Let's go ahead and try something like this. Example. How about f of x is equal to, let's do 2x plus 6 divided by x squared minus 2x minus 15. Okay, how about something like that? Right, I have 2x plus 6 over x squared minus 2x minus 15. Again, you could dive in right now and just try to find your vertical asymptote. What value for x in the denominator makes that equal to 0? You could use some quadratic formula if you really want to go crazy and actually figure it out, but way unnecessary. Let's actually simplify it first, right? Think of, if I asked you what value for x makes the denominator 0, you're probably going to be like, I don't know. Like, that's really hard to see. But we can factor and make that determination a lot easier. Let's go do a GCF in the numerator. Take out a factor of 2, leaves me with x plus 3. In the denominator, let's factor. We have x. We need 1 minus 1 plus, and it looks like we need minus 5 plus 3. And hopefully you can now see, again, matching factor in the numerator, matching factor in the denominator, those cross out. But that cross out does not come for free. That cancellation produces a hole at x equals -3. Okay, so we have to, I always write that note in there just to serve as a mental reminder that I need to go back at the end of my problem and account for the hole in the graph at -3. We're not really going to do anything with it yet, but at the end when I sketch my graph, that's what we need to account for. That leaves me down to 2 over x minus 5. Okay, now what I can do is I can go ahead and actually sketch a graph of that, just like you've done normally with all the other problems. We would say that my vertical asymptote is at x equals 5. The end behavior asymptote is, again, y equals 0 because degree of denominator is larger and there's no vertical shift. So now I would go ahead and sketch my function. So you're going to try to leave a lot of space here. Something kind of like this, and something kind of like this. My vertical asymptote is at x equals 5, so that's 1, 2, 3, 4, 5 right here. My end behavior asymptote is again at 0. That's right here. And now I'm going to go ahead and test some points. So just like before, I mean, this might be old news at this point, but just like before, we're going to pick 2x values to the left and 2x values to the right of the vertical asymptote. So my vertical asymptote's at 5. We're going to go ahead and plug in 3 and 4 and 6 and 7. Okay. 3 goes into my function. I get 2 divided by 3 minus 5. That's negative 2. So I get 2 divided by negative 2 is negative 1. 4 goes in. I get 2 over 4 minus 5 is negative 1. So that's negative 2. So I got 3 comma negative 1, 4 comma negative 2. 6 goes in. We get 2 over 6 minus 5 is 1. So 2 over 1 is 2. And 7 goes in. We get 2 over 7 minus 5. That's 2 over 2, which is 1. So I got a point here and a point here. Okay. And now what I'm going to do is I'm going to go ahead and sketch my curves, approaching but not touching the asymptotes. We just have to remember to account for this hole at x equals negative 3. Wait a minute before you start sketching. Remember to account for that hole. So wherever the curve happens to cross negative 3 on the x-axis, way over here. So wherever that happens to occur, try to draw as neatly as possible. That's negative 1, negative 2, negative 3 right there. I'm going to put an open circle and continue. Okay, to represent the fact that we have one singular undefined point, or in other words, a hole at x equals negative 3. Does anyone have a question, comment, concern about that at all? We're feeling good about that? You feel comfortable? A couple other points I want to bring up. You may ask, well, is it possible that if we factor this down, that these factors actually don't cancel out? Is it possible that we just end up with x minus 5 and x plus 3 in the denominator and they don't cross out with anything? For our purposes in Algebra 2 CP, no, that is not possible. We will always get problems where the factors cancel out to create this hole in the graph. But in the wide world of mathematics, certainly in Algebra 2 Honors, you would explore graphs where you do just have 2 factors of x in the denominator. And what that does is that creates 2 vertical asymptotes in your problem, essentially splitting your graph into 3 regions, a left region, a center region, and a right region. And what you have to do is just plot points for each of the regions to get what the curves look like. The graphs are super cool, but they're definitely complicated. It's outside of the scope of Algebra 2 CP. So for our purposes, when you have to factor, you should notice that those factors always do cancel out. All right, and if they don't, then that's a good indication that you may have factored incorrectly. The other point I want to bring up is about domain and range. Specifically, the domain and range, when we start to have holes in the graph, gets complicated. It gets pretty complicated. So for any problem that does have a hole in the graph, you will not be required to provide the domain and range. It won't even be in the directions. It'll just say provide the vertical asymptote, end behavior asymptote, and hole. Not to say you couldn't do it. In fact, the domain, I think, is something that you probably could do. It's definitely not outside of the realm of your knowledge. The domain, if I go from left to right, take a look. It goes from negative infinity up to this hole of x equals negative 3. So it would be negative infinity to negative 3. Union, negative 3 up to the vertical asymptote of 5. And then union 5 to infinity. So your actual domain, not that you would need to provide this, but it would be negative infinity to negative 3, union negative 3 to 5, union 5 to infinity. That's just a little extra for you, but it's certainly something you can do. The only thing that breaks up the domain are these holes and these asymptotes. Alrighty. The range becomes a lot harder because how do you actually know how high up this hole is, like where it actually is positioned on the y-axis? You're probably thinking, yes, the range is done the same way. You go from bottom to top, you cause a break wherever there's a hole and a break wherever there's an end behavior asymptote. How to figure out where that hole actually is positioned, you'd have to take negative 3 and actually plug it into your simplified version to figure out, hey, where should that hole map to? But again, that's a lot of extra work. That's outside of the scope of what we're really focused on. But I just wanted to mention it because it's something that's possible to do. It's not what you'll be expected to do, though. All right. Anyway, that was kind of a long tangent. But any questions on that at all? Any questions on any of this stuff at all? We're feeling A-okay. We're feeling fantastic. The functions are making sense. Sean's like, "Yup, he's the voice of class, the voice of the class, the voice of reason, not that we deserved, but the one we needed." Sean, thank you so much. All right, in any case, I just want to show you, we have, 3 minutes to go. I just want to show you one quick function as to how you would simplify it, just so there's no confusion about something like this. Okay, how about if I had, I'm not going to do the whole problem out, there's obviously not time for that, but if I had 3x squared plus 21x plus 36, all divided by x squared plus 6x plus 8. What if I had a function like that? Well, that's going to require a little bit of factoring both in the numerator and in the denominator. What I would do in the numerator first is take out a greatest common factor of 3, leaving me with x squared plus 7x plus, 12? And then in the denominator, take out, or actually don't do anything yet. We still have x squared plus 6x plus 8. Now I would factor the numerator and factor the denominator. This gives us 3 times x plus 4 times x plus 3, all divided by x plus 4 times x plus 2. Then you would hopefully notice the x plus 4's cancel out, and you'd be left with the graph of 3 times x plus 3 all over x plus 2, which is a graph that you could do, right? That now has a vertical asymptote of -2. It has an end behavior asymptote of +3 because the leading coefficient of 3 divided by the leading coefficient of 1 would be 3, right? So your vertical asymptote would be x equals -2. Your end behavior asymptote would be y equals 3, and then you would go from there. Plug in points here, and don't forget to include the hole in the graph at x equals -4. Okay? Cool. Just one other common point that I want to make sure I address is what if, and that actually happens in this problem, which is why it's a cool problem. Maybe I'll actually start next class by doing this problem in its entirety. What if the hole happens to be at one of the points that we plug into the graph? For example, in this graph, since my vertical asymptote is at -2, when I create my table of values, I would plug in -4, -3, -1, and 0. That's 2 to the left and 2 to the right of -2. That means that -4, the value that's supposed to be a hole, would actually get plugged into your function. So what do? Well, what you do is you just represent that point wherever it's supposed to be, wherever your table of values indicates that it's supposed to be. You would just represent it with an open circle instead of a closed circle to account for the fact that it's a hole. A lot of times what students do is you actually, if you do this problem in pencil, it's actually a lot easier because what you can do is just draw the graph like normal, and then at the very, very end, wherever the hole happens to be, just erase that little section of the graph and draw in that open circle. A lot of students prefer to do that as well. All right. So that takes us right to the end. One thing that I want to remind you is that there will be practice work. I'll do it right now. I'll post them right now. There will be practice problems posted on Google Classroom for you to try in time for next class. The next time we see each other is on Monday. So try to complete those practice problems for next time. It's only to your benefit to do so. They are not graded, but again, just try your best. The answer key will be provided on Classroom as soon as I'm done with it. I was actually working on it just before this class, so I'm going to get that up to you as soon as it's all set. Make sure you get that progress assessment to me by Thursday night. Please don't forget about that. And there will be another progress assessment coming your way after Monday's class. So that's why it's only to your benefit to practice these types of problems, because you will get them on a graded assignment coming your way soon. Thank you so much for your attention and focus. I don't want to take up more of your time. So have a great rest of your day. Have a great weekend. If you need me, we're here. If you need Miss Mao, she's there. Feel free to reach out. Okay? Thank you so much. Have a great day.